Hi everyone, welcome to my video series. This one is going to be on the physics of music, specifically on the scale. Although I'm going to talk a lot about musical content here, you're not required to know any of this musical content, but I am going to talk about how the scale was developed, and I'm going to talk about the mathematics behind it, the physics behind it. You're going to do a lab about it, which I think is really cool. We're also going to talk about different types of scales. So we'll talk about the chromatic, the pentatonic, the minor and major scales. We'll talk about the circle of fifths, just and equal temperament, and the monochord. So we have a lot to talk about here. But more importantly, we're going to talk about the science behind it, the physics behind it. So I'm going to talk more mathematical concepts here. Here we go. That's what I talked about. So here we go. Okay, so what is a musical scale? A musical scale is a series of notes, and despite maybe not having any musical background, you'll recognize a musical scale. In fact, I will just be silly here and just jump ahead on my piano. And I think you can see it right there. So hopefully you can still hear me from farther away. But a musical scale sounds like this. So I just played what is called the C scale. That's the one that's on the screen that you have there. You don't need to read the notes at all or understand what those mean, but that audible pattern is a scale. Now, I started on the C, but it doesn't matter what note I start on as long as it has that pattern. So in that case, in both of those cases there, come back here, there we go. In both of those cases there, or any of those cases, I played the musical scale. So I'm going to talk about where that scale came from and how it was developed. So it actually came from Pythagoras, and this was a total shocker to me because when I was learning about this, I think of Pythagoras, I think the Pythagoras theorem. That's the one with the a squared plus b squared equals c squared. I think you're familiar with that one. Maybe you're not, but he did a lot of mathematics, and when I heard he did music, it totally shocked me. And he was the one that kind of developed the modern Western scale. And the way he did it, he's made this thing called a monochord, and these are just some examples of what he used. So essentially, a monochord means one string, and what they did was he took that string and gave it some tension. So he actually hung weights. So you can see the weights being hung right here to kind of change the tension. As you might imagine, if you hang something heavier, it's going to be more taut. And he basically changed the tension to give different sounds. But he actually noticed that there was some sort of mathematical reasoning for what sounded good. In fact, this whole development of the scale was all about understanding the universe. So he actually made songs of the heavenly planets because back in the day, the music of the spheres. So if you understood the planets, you understood God. And he wrote a lot of music based on what he think was a heavenly property, which is pretty cool. But coming back to a monochord. So this is the instrument that he actually made that he developed the scale on. So it's really like almost like if you ever take it, I've done this before, I don't know if you have, but if you're taking like a shoebox and you put an elastic band on it, and not a shoebox, or it could be a shoebox, or a tissue box, and you like play it, you're like, oh, I made an instrument, right? Well, that's kind of what this is, but a little nicer. So it's just basically a really thin, taut string with a movable bridge. So I do have that YouTube video to show you, ready to go. Let's get rid of all my other things that are on here right now. Here we go. So we're going to play that. So here we go. So as you notice, it's just two strings and they're the same tone, 1 to 1, right? But then what he did is take a movable bridge, which he's going to demonstrate in just 1 second. So if you see this little piece right here, it can move back and forth. And he found if he put it in a specific spot, it sounded really nice. Turn this up a little bit. It's a little off tune, fun fact. But you get the idea there, is that he found certain ratios that just sounded really nice when he plucked them. 1-to-1, unison, a fifth, an octave, etc. like that. So that's actually what he used. Here we go. And he listened for those nice sounding sounds. So it turns out that those nice sounds only occur at certain mathematical ratios. In other words, the length of the string had a mathematical relationship, which blows my mind. I mean, it's pretty crazy. So he was able to find it. So he came up with 8 intervals. And what I mean by intervals is if I had a scale, each note is 1 interval. So again, you don't need to know how to read music, but if I started on the note of C, the way the scale works, it goes A, B, C, D, E, F, G. My hands don't make any sense. But anyway, A, B, C, D, E, F, G. A, B, C, D, E, F, G. There we go. 7. And then the 8th note repeats itself. In this case, it doesn't start on A, it starts on C. There's a reason for that I'll explain later. But anyway, the interval is where your note is in the scale. So for example, if I say 1, that's your starting note. If I say 5, that's the 5th note from your starting note. So 1, 2, 3, 4, 5. So the G is the 5th note of the C. If I said A is the 6th note of C, etc. So these are the intervals. And at 8, it actually repeats itself. So notice that 8 is over here. So audibly, if I go back to my piano, audibly, the 8th note is called an octave. I hope you notice that it's the same note, but it's just a little higher. So in music theory, if you do music theory, there's actually 12 in the scale because it includes the black keys, but we're not going to include them for now. I'm just going to keep it pretty simple. So the first pattern that he noticed was the octave, or the 8th interval. And he did that when he took the string and divided it in half. So bum, 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 that kind of tone. Just as an example, if you sing this song Somewhere Over the Rainbow, that's an octave. Somewhere over the rainbow. Terrible singer, I know, but that's an octave if you want to know what an octave sounds like. Somewhere, somewhere. Not in tune, but you get the idea. So when you divide the string in half, you make an octave. When you divide the string into thirds, you make the 5th. So the 5th is a pretty famous scale interval. For example, if you sing ba ba black sheep, bum bum, that's a 5th. Or twinkle, twinkle twinkle, just like that. So he noticed if he divided it into specifically a 2/3 ratio. So in other words, when he plucked it, it's really a third if you think about it. When he divided it into a third, he was able to make that 5th sound, and it sounded really nice with the original note. By the way, this is all back to the original. In this case, I'm using the C scale as an example. And then, conveniently, the 4th, if you divide into fourths, it sounds nice, and it's the 4th interval. I think of hark the bum bum, hark the herald angels sing. So bum bum, that's a 4th. I'm trying to think of another 4th. There's so many 4ths in songs. It's hard to pick this one. Bum, the 6th. Here's the 6th. Bum bum. Hold on. Bum bum bum. That's the 4th. A B C. If it's A B or NBC, I don't know what that news channel is, but I always remember the 1, 6, and 4. Bum bum bum. So those audio cues are really helpful for sight singing, which I am working on, as you can see. But anyway, so this is where you would play them. If you know solfege, that's when you say do, re, mi, fa, sol, la, ti, do in place of the intervals. Do, do, do. I need a note. Here we go. Do, re, mi, fa, sol, la, ti, do. It's helpful to have a note when you sing those. But anyway, the do is the first note. Mi, re is the second, but mi is the third. The fourth is fa, and sol is the fifth. So do, fa, sol. So do, so, fa. So those are the notes and where to play them if you were to play them on the monochord string. So we also have what is called a musical ratio. So when you're dividing those strings, you always take the bigger number and put it on top. So unison means just the open string. The octave is when you divide the string in the half. The fifth is when you divide it into thirds, and the fourth is when you divide it into fourths. So we take the bigger, notice we're taking the bigger number and divide it by the smaller number, and we get what we call musical ratios. So anytime you have a note that has the ratio 2, it's by definition an octave. And if you have a note that has a ratio that's 1.5, by definition, that is a fifth. And in fact, your lab will actually do that as well. You're going to take two frequencies and divide them and find out which of those notes that you play are the fifth or the fourth or whatever. Ooh, excuse me. So notice I marked them here. So again, you don't need to know how to read music, but you can see the notes are gradually getting higher. In other words, they literally are going up in pitch. And in fact, it is this note. This is number 1. So, do, fa, sol, do, do, fa, sol, do. Those are the notes. Having fun singing. I'm sorry. I know I'm terrible. I know some of you could probably sing much better than I can, but I enjoy singing, despite my ability. But anyway, so notice that we're missing these, right? We're missing 2, 3, 6, and 7. And I noticed I highlighted that and animated all of that fun stuff. Turns out that he figured out a really clever way to find the next notes to fit nice and perfectly, to sound good. I'm not going to go crazy into how he did it, but he did a mathematical logarithm basically to kind of figure this out. He took the first ratio and he either multiplied or divided it by 3 halves, and then if it was too small, he doubled it, and if it was too big, he halved it. And I'm going to leave it at that. If you're really interested, I'd be happy to describe how he actually did it, because it's a little more, it's pretty complicated mathematically, but in the end, he came up with this. Doing his method all mathematically checks out that the ratio, if I divide 2 frequencies, it gives me these interval ratios. So an interval ratio of 5 is 1.5. The interval ratio of a third, or 3, is 1.88. So as long as you have that ratio, you are by definition a third compared to your note. Now, the other thing that we're dealing with is the major scale, or a septonic scale. Septonic, of course, sept means 7. And if you notice, it's pretty much 7 notes except for the 8th, which repeats itself. This is also known as the major scale. It's a scale that you all know with do, re, mi, and all that fun stuff here. So I'm going to talk about other types of scales, but before I do, I have to talk about these things called whole tones or semitones. So if you're looking at a piano, so a little piano lesson for you, we have these things called intervals, and they're called semitones and whole tones. Now, when you look at them on a piano, the semitones are the notes next to one another, also known as half steps. So if you look at the B and the C, it's a very special part of the piano because there's no black key in between them. And because of that, it goes from B to C without going to another note. So this is what we call a semitone or a half step. Notice that you can have a half step in other places, but notice that here it's going to be F sharp to G. That this is a half step because it goes from one note to the next note. So G to G sharp is a half step. G sharp to A is a half step. C to C sharp is a half step. D flat to D is a half step, etc. I hope you notice that basically as I go up or down, that is called a half step. A whole step, and notice the steps is one, right? So I'm only going up one step if you think about it. Up or down, it doesn't matter. When you do two steps, you're called a whole tone. So if you do a whole step, if I start on A like this diagram shows, notice I go to the B flat and then to the B. That's 1, 2 steps. That's a whole tone. And in fact, if I start on C, the whole tone would be to the C sharp to the D. So that's a whole tone right there. From here to here, from D to E is a whole tone. Now, from E to E sharp, F sharp is a whole tone. Notice I have to go 1, 2 steps. And if I were going to go a whole tone here, it'd be 1, 2 steps. Whole tone, 1, 2 steps. Whole tone, 1, 2 steps. So I hope you notice the difference. Now, it turns out that anytime you go up a whole tone, you always will make this specific ratio, 1.1225. So in other words, if I were to play two tuning forks, actually, these happen to be the case. This is a D and a C. And they're a whole step. So in other words, if I take the frequency of the D, 288, and divide it of the C, 256, I don't know if you can see my calculator, dramatic. See, I divided it. You can sort of see it. There it is, 1.125. That's what I mean by the ratio. I don't have one example for the semitone at the moment. So the pattern of whole and half steps give defining features of what we call the scale. So the major scale is derived of this following pattern: whole, whole, half, whole, 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 half. And you can see it on the piano. On the piano, you're basically, for the C scale, playing all of the white keys. This is, in fact, the major scale. I'm going to go ahead and move my camera again because I just happen to be in the piano room, where is my piano? There we go. Like this. And it's better if you can see. There we go. So, as you can see, playing all of the white keys. I know it's kind of hard for you to see the camera right there. Now I can cheat. In fact, I do when it comes to playing scales. As long as I follow that pattern, whole, whole, half, whole, 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 half, I can play any major scale. In fact, I will play for you live a major scale that I don't play regularly. But because I know the pattern, I can fake it. I'm going to play the B flat major scale. Good luck. So I gotta go up. That's my starting note. I really don't know how to play this. I just want you to know that. I'm gonna figure it out. So there's the B flat. The whole step is here. Whole step. Whole step. Oops, see? Half step, that's why. Whole. Hold on. Whole. Whole. Half. Whole. 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 Like a genius. I don't know that scale. I did know the pattern though, except when I messed up. So that's what how I could figure out any scale. Just based on the pattern. I could start on any note. I don't have to start on C. I can start on D. I can start on F. If I start on F, it sounds like this. There you go. That's better. If I start on G, it sounds like this. A. And back to C. You can hear them getting higher, but you get the point. So I'm going to move on. If you look at the minor scale, notice the pattern changes, and the way it sounds doesn't sound like that major scale. I'm going to play the major scale and then play the minor scale so you can hear the difference. So the major scale for C, the minor scale for C. Different, right? Almost darker. I like minor scales, those are my favorite. Sorry, I got carried away. But it's so cool, right? So, same thing. I don't know very many minor scales, to be quite honest, but I can make that sound if I follow the pattern, the whole, half, whole, half, whole. I'm going to start on A flat. I've never played this minor scale before, but I'm going to follow that pattern. So here's my first note. I go whole, so it's this one, then half, then whole, then whole, then half, and then whole. Weird, right? I played it right. It's crazy. That's the minor scale. A really easy minor scale is the A scale, all white keys, starting on A. There you go. Chromatic is the easiest scale you can play. You can impress your friends by just going up every single note by a half step. Oops. There you go. That's chromatic. I can go all the way up. So, chromatic just means you go up by one step each, a half step each time. So notice the pattern is actually pretty silly. It's just one, and it's 12 notes because I'm playing all the notes in between. So like that. So if I started on an E, it would be all the notes between here and the next E. Like I said, it's a super easy scale. I don't need to know much about it. Pentatonic. It has an interesting kind of sound to it. You've heard it before. Sounds really nice. That's a pentatonic scale. But we do a weird thing. So I start on the C. I go whole step, whole step. Then I do 1 1/2, a whole and a half. So I go up 3 steps. And then I do it again. So I go up 3 steps. That's a pentatonic scale. Very, very famous. If you listen to classical pieces, they use it a lot. And in many cultures, they use the pentatonic scale. Oops. So, there we go. Ooh, the blues scale. Same thing. You got that weird 3, the whole and a half. So here's the blues scale. I'll play it for you. Sounds bluesy, right? I had to fix it, but there you go. Anyway, you get an interesting pattern with this. You do that 3-step first, then the whole, then a half whole. So that's a blues scale for you. And this one also, just like the pentatonic. So pentatonic, of course, pent means 5, the 5-note scale. This one also is a 5-note scale, but it has a, a variation to it. So I think, no, I'll stay here for a second. So if you do it stepwise, this is how each of the scales work. There are many, many, many scales. In fact, there, as you can see, there's even more scales. I'm not going to test or quiz you on the more scales, but I am just going to make you, I just want you to be aware that there's more different types of scales. So if you go into like a music theory course, you'll look, you know, you do the Mixolydian or the Aeolian and all these other kind of crazy scales that you learn depending on what you're playing. So in class, I would partner you up and actually have you calculate some of these ratios and actually figure out what, you know, if there is any intervals, what they are, etc. like that. So we're gonna, of course, skip this, unfortunately. I'm gonna move my seat. Sorry about that. There we go. But let's just pick two notes. So I'm gonna pick the 466 and the 659. So 659 divided by 466 gives me a 1.4. So I know for a fact that that in fact is not any of the scale ratios that we have, right? This is not an interval. In other words, this wouldn't be any one of these. So it's a class exercise we would have tried to do. I share this video in class. I'm not going to share it on this video. It takes it's 5 minutes. It's incredible. Watch it. But he demonstrates the pentatonic scale and how, despite our tone deafness that we have, right? Some people claim that they're tone deaf, but in fact you're not. You can recognize sounds. You know your mother's voice from a phone versus in person. You know how things sound, you know, the sound of a teapot, you know, so you're not tone deaf. In fact, all of us know the pentatonic scale, whether or not you know it, and he demonstrates that. It's just really fantastic. So definitely pause it and watch it, or watch it at the end. It's definitely worth watching. I talked about the fifth interval, right? And I actually alluded earlier that the fifth interval from the starting note C is the G. So this is a handy tool that musicians use called the circle of fifths. And depending on what your starting note is, the next note is the fifth. So if I chose the C, the fifth note of the C is the G. Now we go like a clock, so we're going clockwise. So if I started, for example, on this A flat, the fifth is going to be the E flat, not D flat. And then all of this, A minor, the fifth is E minor. So you can use this. So I have a couple questions just using this musical scale. So I'm going to talk about what is called the just scale. So the just scale is everything that I've been talking about so far. It's derived from the monochord and vibrating strings. Now it turns out that when you have something like a string, you have the ability to change the length ever so slightly so that you get the right tone coming out. And this is called the just scale. So orchestras do this, instruments do this. But when it came to developing the piano, to keep the intervals the same across many different keys, you can't do it. So just like what I just did on the calculator, in other words, when I took those two numbers and I divided it and I didn't get a scale interval, like I got 1.4 instead of 1.33 or 1.5, that means it's not a perfect fourth or whatever the number I was trying to get. Point is, it's out of tune. So things that are naturally out of tune because of the engineering and the sheer ability are pianos and guitars. So an equal tempered scale sounds slightly off than a just scale. I'm going to give you an audio example of this, in fact, because it's just interesting to know this. So just tonic means if I were to use the monochord or play on an instrument. And this is what happens when you play on a piano or a harpsichord.
This is the sound and visual image of a pure harmonic third.
Alright, I'm going to go ahead and stop it at this point. Oops. Of course, this video goes on for a little while longer. It's pretty cool. I totally notice a intonation with my piano. It drives, well, my piano is actually out of tune, but it's also out of tune because of this. It drives me nuts that I can't have that true ring. I wonder if you were able to hear it too. The difference between the nice tone and the not so nice tone, right? You don't need to know any of this stuff. This is just in case you're curious about it. But what I'm trying to show you here is you have what is called the just scale, and these are the ratios that I kind of talked about already, like the major second. But on a piano, and this is because in a piano you have to change scales. You can change, any of your scales. And because the lengths are not perfectly the same for each scale, it kind of messes things up. So the good thing is the octaves usually ring true and the unisons, but you can see even the minor second, they're not the same, and that the major third are slightly off. You can see the numbers here when they do it out. Even the fifth is disturbingly, it's not off by a lot, but it is not the same if you notice. So people can hear the difference between playing with an instrument that can play, any scale versus an instrument that plays multiple scales like a piano or a guitar. And, the difference between the two of them are right here, and you could even go into more music theory about the sense. This is just in case you're curious. I'm not going to actually go into it, but it gets really complicated really quickly. And we're on to our, pretty much our last topic here is chords. So let me go back to the piano. Okay, back to the piano. And chords are just this, this nice musical quality where they sound nice. So I'm playing what's on here actually. So here's a major chord. Sorry, I muted it. It sounds nice. I could play other things. As you can see, it doesn't sound as nice as the nice major chord I have here. I can play the minor chord. Ooh, I like that. It's so nice. The diminished. The augmented. And then the last one, I can't read it, the major. Like that. And I could do the one on the bottom. Sounds like this. And then I could do, I like that one. And the next one is, and then the second to last one is, I like to play that. There we go. And then the very last one sounds like this. So there's all different types of chords, and of course they sound different, they have different flavors, but the main one is the major chord. Songs are like that. It sounds like I know a song, right? Anyway, I just made that up. But the point is that they sound really good. These are also called triads if you do them in groups of 3. Now, there's a reason why those chords sound really nice together. It's all physics. Exciting, right? Turns out that if I were to take that program that I used a while ago for the tones, where I could pick out the 2 tones, for some of you may not have done that lab, but for some of you I know you did that lab. But anyway, if I were to play this piano note like this, you wouldn't see one peak, you would see actually many peaks, because the piano actually has different harmonics. So the tonic note, the first one, has a set of frequencies. You can see them in the top row right there. You can see my mouse up top here. If I play the 5th, it has certain frequencies too. But if I play the 2 together, it sounds nice, right? Well, it also sounds nice because if I hope you notice that the 5th and the tonic both share the same frequencies, 792. 1584, 3168, and those reinforcements really sound nice to the ear. And if you look at the triad, you get basically 3, you get more of those overlaps and reinforcements, which makes them sound nice. So that's the reason why chords sound good. An inversion is when you take the chord and place the tonic note in different spots. So here's the root position. Oops. One chord inversion, and another one. Just like that. They're all the same, they're the same notes in the chord, but they just played in different order. And they all sound really nice, regardless of the order that I played them in. And again, this all has to do with the reinforcement of certain frequencies, reinforcement of the harmonics that are present in those frequencies, in those notes. And this is just reiterating the same thing, depending on the type of chords that you play. Like that. Again, another thing I would share with class, it's amazing, it's amazing. He's such a good speaker about classical music. Definitely watch it. I'm not going to watch it here now, but it's definitely worth watching. It's really cool. And just in case you want to go further into the rabbit hole of musical scales, there's some more there. So just to summarize, musical scales was developed by Pythagoras, and he used a monochord and figured out what sounded nice. And it turned out that those nice sounding chords actually had mathematical relationships that Pythagoras just loved to figure out, and he found. And he developed the modern Symphonic Western major scale. So I talked about all different types of scales, and they're all based on their patterns of whole and half steps. The interval ratios are based on taking 2 frequencies and dividing them by one another. They're also divided, they're also by the string lengths too, by the way. I didn't really mention it before, but I'm going to mention it now. But you're going to do a lab, if you haven't already done so, finding those interval ratios and deciphering the scale and what notes you're playing and hoping that they match. It's pretty fun. And lastly, that harmony is based on reinforcing those harmonics, and the more you reinforce, the nicer they sound to your ear. So that concludes the video on the physics of musical scales. Let me know if you have any questions. Have a nice evening.